In this video, we are going to dive into the world of Autoencoder and going to build one using TensorFlow and the Keras API. An autoencoder is a class of neural network for which the input is same as the output. This works by compressing the input into a latent space representation and then reconstructing the output from this representation. Hi, this is Nikhil Toma and you are watching Idiot Developer. Make sure that you subscribe the channel for more deep learning videos. In this video, we are going to build a deep autoencoder in TensorFlow using Keras API. So let's start the code. First of all, we are going to import all the required packages and libraries and functions which we are going to require for this code. First package is the OS module. And here we will write tf.cpp, not dot, that is underscore cpp min log level is equals to 2. So that we can get rid of the unwanted TensorFlow messages and warning. We just want to see our content. Next we'll import the numpy. Import matplotlib dot pyplot as plt. Okay. Next is the TensorFlow. And after that we are going to import some layers from the TensorFlow Keras API. Input layer we are going to use to create the input to give the MNIST dataset images. And next is the dense. As I've already told you, we're going to make a deep autoencoder, and for that we're going to use the dense layer. So here we're going to have an input layer and output layer. So the input and output are going to be same, and in between that we are going to use multiple hidden layer. Next we're going to import the model function. From TensorFlow. Now we are going to import the Atom optimizer for optimizing our architecture. Okay, so we have finished importing all the things. Next, let's seed the environment first. We are going to seed the randomness because we want the result to be reproducible. Maybe in this program we do not require that reproducibility, but still in deep learning project, make sure that your result, your code is reproducible. Otherwise it would be a problem, because on my system I'm getting different result, on your system you're getting different result, and all this is because of the randomness. So make sure that you seed the randomness, so that we, if I try this program on my system and you try on your system, we should get the same random numbers generated. So that's why. And there are weights in the dense layer which are randomly initialized, so make sure that you seed the program first. First we need to seed the numpy randomness, and you need to provide a number here. Just that. Okay, so we have seed both the things. Okay, should be set seed. Okay, and you already know we're going to use the MNIST dataset, so it won't take long to train the dataset. It would also be easy. Now let's load the training and the testing dataset. So this is the training images. X basically refer to image and Y refer to labels, but for this video we only require the images. X test and Y test. So this is the testing data. So here the training data set consists of 550,000 images and label pair, and for the test data set we have 10,000 images and label pairs. Let's now normalize the image pixels for the training and the testing dataset by dividing them with 255. Okay, now the value of the image pixels are in the range of 0 and 1, and this would make it easy for the model to converge. If you don't try to normalize your pixel, then it would take a long time for your model to converge. Now next, just specify the height and the width. So height and the width for the image for the image, the MNIST data set is 28 by 28 and the channel is 1. Let's specify that also. Next, we're going to flatten the images. Flattening. Now correct, flattening. Extreme. Going to be, let's reshape them. First of all, the variable xtrain. Second, the shape in which we want to reshape them. -1 height multiply width. Let's say multiply channel also. So I'm writing channel is equals to 1. Maybe you can ignore for the MNIST, but in case like CIFAR 10, CIFAR 100 or any data set which has RGB images, so it would be 3 here. So that's why I'm writing C here. In case of grayscale, it won't make much difference if I remove it. But in case of an RGB image, it would make difference. Your program would be incorrect. The reshaping would not take place correctly. Okay. Now same for the test. Xtest is equals to np.reshape xtest -1 height into width into channel. Now if you don't know what this -1 refer, it basically refers to its value remain the same as it is. So it is 50,000 comma like 28 by 28 refer to maybe 784. Yeah, so its shape would be what I see 50,000 by 784, and here it should be 10,000 by 784. So let's print the shape first. Xtrain dot shape and xtest dot shape. Okay. Okay, that is incorrect. Spelling mistake is there. It should be ENVIRON. Okay, environ. Okay, let's again run it. I think the program is working, but we have to wait for some time. Okay, so it is 60,000 images. I said 50,000. I'm sorry for this mistake. It's 60,000 images for training and 10,000 for the testing. Okay, so everything is correct till now. Now let's specify the latent dimension. That is the latent space representation. We're going to compress the original input into a small compact form that we call the latent space or latent dimension. Latent dimension, let's say 32. So now we're going to build the autoencoder. Building the, okay, spelling mistake. Autoencoder. First of all, you can specify the inputs. An input is going to be a flattened shape. I've already told you what the shape is. Height into width into the channel. Next is going to be an encoder. Okay, and let's say we're going to use a dense layer. The number of node, let's say, is 256. Okay, and activation is going to be ReLU and inputs, and this is H refer to hidden state, or we can say the latent space representation is determined by this layer. Again, activation is going to be ReLU and input is going to be E. E refer to encoder. So D refer to decoder, because we again need to reconstruct the image. Okay. Again we are going to increase the number of nodes in this layer, and activation is going to be ReLU. Now here comes the last layer, that is output layer. It's going to be a dense layer again, and the output should be same as input. So this is height into width into number of channels, and activation here changes to sigmoid, because as we know we have normalized the image pixel in the range of 0 and 1. So we also want the output pixel values in the form of 0 and 1. So for that we're going to use sigmoid. Okay, now we have done this. Now we're going to build the model using the model function which we have imported, or model class we can say. It's not a function, it's a class. First it's going to take the input and then the output. After that we can also give it a name, Deep Autoencoder. Okay, now let's print the summary, autoencoder dot summary. Let's run it again and see if everything is fine till now. Okay, there's some issue. Check, but okay, I know. Here in case of output we haven't specified any input, and its input is going to be the decoder output of this decoder layer. Okay, so here you can also add more layers, but for this demonstration I'm going to use only 3 layers. Okay, and the last is going to be output. So basically 5 layer. First input, then an encoder layer, a hidden representation layer, a decoder layer that is going to reconstruct, and the output layer which is going to give the final output, that is the original input, the reconstructed original input. And that original reconstructed input, the reconstructed input would not be absolutely the same copy. It would try to minimize the loss, the difference between the original and the output, but that would not be exactly the same. It would still have some difference, and we're going to see them after we're going to train this model. Let me just run this code and check for any error again. Okay, so you can see the model is completed, and the parameter are 4,19,120 parameters are there. As we are using dense layer, dense usually are very highly compact layer, and they have very large number of parameter if we compare them to convolutional encoder. Not the convolution encoder, the convolution layer. In convolution layer the weight is shared, so that's why they have less number of parameter and they're more efficient. So in the next video we're going to see how we can build an autoencoder using the convolutional layer that we call the convolutional autoencoder. But for this let's get back to the deep autoencoder. So now we're going to train the autoencoder. Using the fit function. First the input, second the output. So input and output are going to be same. Next is the number of epoch you want to train on, and after that is the batch size. We need to specify that, let's say 256. Shuffle, okay, it should be h. Shuffle is going to be 2. We want to shuffle that data set. Okay, after every epoch is completed we want to shuffle it. Now comes the validation data set, and for validation we're going to use the testing data set provided by the TensorFlow. Okay, now we can train the data set. Let's now write again the code. Now till now let's imagine the model is trained. Now we're going to write the code for predicting. So we're going to predict again on the test data set that we have used for validation. Or you can, if you just want to use separate data for validation and testing, you can split the training data again and convert it into a form. Like there are 60,000 images, you can use 50,000 images for training and rest 10,000 for validation, and testing data set is provided separately. So it's up to you, but for this I'm going to use same data set for validation and testing. So let's now imagine the model is trained and we are predicting. Autoencoder dot predict. and we use the test dataset. Okay, and now we're going to use the matplotlib library to plot these images. So how many digits we want to display? Let's say visualize. We're going to visualize these images. So we want to display 10 images. Let's say 10 digits we want to display. plt.figure fig size is going to be, let's say, 20 by 4. Okay, now for I in range n, we want to display 10 images. So let this first we want to display the original image. Display original. Again, here we're going to create a subplot 2 comma n I plus 1. Okay, it should be I plus 1. Okay, next we will set the title and it should be original image. You want to see which one is original and which one is reconstructed or the predicted image. Okay, now we need to set the image into this subplot xtest I dot reshape. As we know, the image is in the form of 784. It is flattened. Now we need to just reshape it again to height comma width. As the image is grayscale, so you need not to provide the channel here. And if it is a 3-dimensional image, like it are 3 channels, so you need to specify the number of channels also here, but we will not specify because it is not required. We want to print this as a grayscale image. plt.gray. And you can also remove this function if the image is a 3-dimensional, not 3-dimensional, it has 3 channels. Okay, let's do some more thing. So we're going to set visible. So we're going to make sure that the axes are invisible. Okay, should be set visible false. Okay. And same for the y. ex dot get y axis set visible to false. Okay, now like this we are going to display the reconstructed part, reconstructed images or the predicted image. Let me copy this again. Okay, now it's 2 n I plus 1 plus n. Okay, instead of original we need to say predicted. Okay, now again we just need to change this x test to test pred y. Okay, everything going to same. We're going to reshape it grayscale. Now here we need to just save the result. plt dot save fig. Okay, let's save the figure. Let's say it deep autoencoder da.png. Now we're going to run this program and train it and see how it performs. And we have forgot one important thing. We haven't compiled the model. And these are common thing which everyone does, and I also do this. Not a problem. First of all, we will specify the optimizer as Adam, which we have already imported above, and the learning rate we're going to set is 1e minus 3. Second is the loss. As we are using the sigmoid as the output, so we're going to use the binary cross entropy as the loss function. Now it is compiled. We can run this again and let's see if there's any error. Okay, again there's an error, value error, deep autoencoders. I think this is the name, and I think if we just need, I think it doesn't need any space or anything. Let's see, otherwise we will remove it. It's not that important giving name. Okay, it's the space which is causing issue. You can see model name deep underscore autoencoder, and here you can see it is training, and you can see that the loss is decreasing, and even the validation loss is very less. It's training much faster. So within a few seconds it is going to be completed. So it would take 50 seconds. So even you don't have a GPU, you can train it on CPU. But I would say if you are training on a much larger data set, don't use a CPU. It would heat up and may cause problem. So always try to prefer a GPU for machine learning. Okay, so the training is completed. We can see our result, that is Deep Autoencoded image. Okay, so you can see the top ones are the original images and the bottom one are the predicted images. So you can see they are same, but in some place they are not of a perfect match. Like you can see in 4 there is a little bend here, but in the predicted image there is not that bend. And in 9, the next is, you can see in the predicted image some some values are missing. Okay, it has not predicted that correctly. So like this, there's going to be some small difference in the images. So we have reached the end of the video, and if you have reached the end, this means that you enjoyed the video. And if you like the content, then please subscribe the channel, share the video with your friends and on the other social media platform, and help me to grow my channel. And please make sure you watch all other videos also if you want. Thank you. Have a nice day.